Hello everyone, welcome to today's presentation. In today's video presentation, we are going to discuss about supercapacitor. The outcome from this presentation is we'll have an understanding of what are capacitors, then we'll see what are supercapacitors, how do they work, what are its advantages and disadvantages, and finally a comparison with the conventional capacitors. So let's begin. So an introduction to capacitors. Capacitors are electronic components that store electrical energy in an electric field. They do not produce electrons. They are the passive components of electrical system. They are made up of two closed metallic conducting plates that are usually separated by a non-conducting substance or a dielectric material. Though any non-conducting substance can be used as a dielectric, practically, some special materials that we use are porcelain, mylar, Teflon, mica, cellulose, and so on. A capacitor can thus be defined by the type of dielectric selected. It also defines the application of the capacitor. According to the size and type of dielectric used, the capacitor can be used for high voltage as well as low voltage applications. For applications in radio tuning circuits, air is commonly used as a dielectric. In timer circuits, mylar can be used as dielectric. Similarly, for high voltage application, glass is normally used, and for the application in X-ray and MRI machines, ceramic is mostly preferred. Thus, the dielectric material is the main substance that helps in storing the electrical energy in a capacitor. Now, how does it work? When we connect a power source or a battery to the metal plates of a capacitor, a current will try to flow, or the electrons from the plate connected to the positive lid of the battery will start moving to the plate connected to the negative lid of the battery. However, because of the dielectric medium present between the plates, the electrons won't be able to pass through the capacitor, so they will start to accumulate on the plates. After a certain number of electrons get accumulated on the plate, the battery will have insufficient energy to push any new electron to enter the plate because of the repulsion of those electrons which are already there. At this point, the capacitor is actually fully charged. One plate has developed a net negative charge and the second plate has developed an equal net positive charge, creating an electric field with an attractive force between them which holds the charge of the capacitor. A dielectric contains molecules that are polar in nature, which means that they can change their orientation based on the charges on the two plates. So the molecules will align themselves with the electric field in such a way that they will enable more electrons to be attracted to the negative plate while repelling more electrons out of the positive plate. So once the capacitor is fully charged, if we remove the battery, it will hold the electric charge for a long time, acting as an energy storage device. Now, if we shorten the two ends of the capacitor through a load, say an electric bulb, a current will start flowing through the load. The accumulated electrons from the first plate will start moving to the second plate until both plates become back again electrically neutral. This can be seen from this diagram, in which initially the bulb will glow with a high intensity when the capacitor is fully charged. Now, as the accumulated charge density starts to decrease slowly by the glowing of the bulb, its intensity will keep on decreasing and finally it will turn off when the capacitor will get fully discharged. Now, supercapacitors. After having an understanding of capacitors, it will be easier for us to understand what supercapacitors are. A supercapacitor is also sometimes called as ultracapacitor or a high capacity capacitor or a double layer electrolytic capacitor that can store large amount of energy, nearly 10 to 100 times more than that which is stored in the electrolytic capacitors. It is specifically designed capacitor capable of storing enormous amount of electric charge. They offer operational voltage of range between 1 volt and 3 volt for both aqueous and organic electrolytes. It also promises great potential for rapid charging and energy storage. It is widely preferred than batteries because of its faster charging capacity and faster delivery of energy. It has more charging and discharging cycles than rechargeable batteries. The main advantage of this type of capacitor is its efficiency and the high energy storage capacity. Similar to a normal capacitor, the supercapacitor is also having two parallel plates with a much bigger area and shorter distance. The plates are made up of metals and soaked in electrolytes. The plates are separated by a thin layer called an insulator or dielectric material. The plates are made from metal coated with a porous substance which are powdery activated charcoal, which effectively gives them bigger area for storing much more charge. In an ordinary capacitor, the plates are separated by relatively thick dielectric made from something like mica, a thin plastic film, or even simply air. Unlike other capacitors that use the conventional dielectric, these supercapacitors employ two methods for storage of electrical energy, that is, pseudo-capacitance and double-layered capacitance. Pseudo-capacitance is originally electrochemical, while double-layer capacitance is electrostatic. Very high capacitances like 12,000 farad can be achieved using this capacitor technology. When the capacitor is charged, positive charges form on one plate and negative charges on other, creating an electric field between them. This field will polarize the dielectric, so its molecule will now line up in the opposite direction to the field and reduce its strength. That means the plates can store more charge at a given voltage. In a supercapacitor, there is no dielectric as such. Instead, both plates are soaked in an electrolyte and separated by a very thin insulator which might be made of carbon, paper, or plastic. When the plates are charged up, an opposite charge forms on either side of the separator, creating what's called an electric double layer, maybe just one molecule thick, as compared to a dielectric that might range in thickness from few microns to millimeter or more in conventional capacitor. This is why supercapacitors are often referred to as double-layer capacitors or electric double-layer capacitors or EDLCs. The capacitance of a capacitor increases as the area of the plates increases and the distance between them decreases. In a nutshell, supercapacitors get their much bigger capacitance from a combination of plates with bigger effective surface area because of the presence of activated carbon or charcoal in its construction and the less distance between them because of their very effective double layer. As discussed, standard capacitors are made up of two metallic plates or electrodes that are separated by a dielectric substance between them. Upon application of voltage, electrons accumulate at one of the electrodes, thereby storing the electrical charge. Meanwhile, dielectric material that is wedged between the electrodes undergo process called dielectric polarization and they help to increase the capacitance. This can be seen from the figure. Supercapacitors have two parallel plates with a bigger area and the distance between the plates is small. The plates are made up of metals and soaked in electrolytes. The plates are separated by a thin layer called an insulator. The plates are made from metal coated with porous substance such as powdery activated charcoal, which effectively gives them bigger area for storing much more charge. Both plates are soaked in an electrolyte separated by a thin insulator layer which is made up of carbon, paper or plastic. When plates are charged up, an opposite charge forms on either side of the separator, creating what's called an electric double layer. This is why supercapacitors are often referred to as the double-layer capacitors or electric double-layer capacitors. The capacitance of a capacitor increases as the area of the plates increase and the distance between them decreases. In a nutshell, supercapacitor get their much bigger capacitance from a combination of plates with bigger effective surface area and less distance between them, which is because of the very effective double layer. Now this double layer structure can be seen from this figure, where we can see a double layer structure has been formed, and this is the electrolyte, and in between we have a separator. Supercapacitors also work basically on the same principle as normal capacitors, except that the wedging material is an electrolytic solution rather than a dielectric substance. On application of voltage, an electric double layer will be created that aligns both positive and negative charge along the boundary of electrodes and electrolytic solution. This place acts as a warehouse for storing electric charge. The supercapacitor's capacitance is in direct proportion to the area of electrical double layer. The activated carbon is non-porous material and has many surface holes that help in covering a big surface area. Due to electrolytic solution and electrodes, supercapacitors share the structure of a typical battery for electricity storage. While chemical reactions take place between electrolytic solution and the electrode in a battery, supercapacitors allow only electron movement between electrodes. These differences result in the varying properties between a battery and a supercapacitor. Now, what are the basic types of supercapacitors? Supercapacitors can be classified into three types: double layer capacitors, pseudo capacitors, and hybrid capacitors. Double layer capacitors are storing charge on the basis of electrostatic form, whereas pseudocapacitors store charge electrochemically, and our hybrid capacitors are a combination of the first two, and they can store charge both electrostatically as well as electrochemically. Now, what advantages do these supercapacitors offer as compared to other capacitors, that is ordinary capacitors or battery? They have long life. They have higher efficiency, their charging rate is rapid, they are available at lower cost, they have high power storage, they have faster release, they are lightweight, small in size, and can withstand a temperature range from -30 to 65 degrees centigrade. Now, few disadvantages. It has the highest dielectric absorption of any type of capacitor. Its self-discharge rate is higher than the electrochemical battery. Cells hold a low voltage. Serial connections are needed to obtain higher voltage. Voltage balancing is required if more than 3 capacitors are connected in series. Due to rapid and large release of energy, EDLCs have the potential to be deadly to humans. That is, they are very dangerous to humans. Now, few of its applications. Some of the earliest uses were motor startup capacitors for large engines in tanks and submarines. They are used in electric vehicles which make use of regenerative braking mechanism to charge it in a very short time. China has been experimenting with a new form of electric bus called Kappa bus that runs without power lines using large onboard EDLCs. Germany has operated a light rail vehicle that uses EDLCs to store braking energy. They can be used in PC cards, flash photography devices, in digital cameras, flashlights, portable media players, and in automated meter reading, particularly where extremely fast charging is desirable. They are used as backup energy source for GPS-guided missiles. They are also used in portable gadgets and devices. Now, its comparison with capacitor. If we try to compare a capacitor and supercapacitor, then we can see following points are the main criteria or main areas of comparison. First, in terms of definition, if we see, capacitors can be said to be passive electrical device that stores energy in its electric field, whereas supercapacitors also store electrical energy, but they differ from ordinary capacitor due to its high capacitance. Construction-wise, a capacitor consists of two parallel conducting metallic plates with a dielectric medium in between them, and electrical energy is stored in the electrostatic field in it. Whereas in supercapacitors, again they are made up of two metallic plates which are coated with activated carbon or charcoal and has electrolytic solution in between them instead of a dielectric material. Dielectric medium, in case of a capacitor, aluminum oxide, polymer films or ceramic are used as a dielectric medium commonly. But in case of supercapacitors, activated carbon acts as a medium. When voltage is applied, double electric field is generated that acts like a dielectric medium. Now if we see about the energy density, capacitors have very low energy density compared to supercapacitors. Cost, capacitors are comparatively cheaper than the supercapacitors. Voltage capacity, capacitors have high voltage rating, whereas supercapacitors have very low rating, usually of range 2.7 volt. Energy storage, in capacitors it is stored within the electric field, whereas in supercapacitors it is stored within its double electric field, which is due to the presence of carbon. Charge and discharge rate, capacitors have a faster charge discharge rate, whereas in supercapacitors charging rate is faster but discharge rate is slow. Capacitance, for normal capacitors, capacitance is comparatively low, whereas supercapacitors have extremely high capacitance. Specific energy, in case of capacitors it is high, whereas in case of supercapacitors it is low. These were some of the comparison criteria among capacitors and supercapacitors. So that's all for today's session. Have a nice day and thank you.